Thank you for the introduction. With this talk, we kind of change a bit topic and talk mainly on carbon material in long dimension. So I don't think I have to spend a lot of time here explaining the graphene was the first 2D material that was experimentally obtained, but this is only the 2D, a lot of carbon. You can also have 1D graphene nanoribbon or nanotube, or 0D fullerene, graphene quantum dot that have many different names, can be considered also as molecular graphene or PAH or you name it, but they are all the same, a small graphene essentially chunk. And we can also consider as 0D material some small molecule semiconductor that can be either donor or acceptor. While those systems are interesting by their own, if you put them together to make an heterojunction, then you have very interesting property because you can synergetically enhance, for example, optoelectronic properties. And if you focus on optical property, you can enhance the visible electroluminescence or the near infrared one, or you can enhance the photocurrent generation. However, for a computational point of view, this is tricky because if you consider a 3D bulk system, if you focus on the optical property, like for an exciton, you have one remote exciton is very broad, weakly bounded. And for the other hand of the scale, if you consider organic crystals, you have Frankel excitons, where your exciton is localized on one molecule, the binding energy is very high. And if you consider different dimensionality that go together to generate this heterojunction, you have somewhere in between. So it's not so straightforward for computation to figure out which one is the best description, and perhaps it's something in between. So there is room for development here. When you generate this heterojunction, depending on the alignment of the energy level of the frontal molecular orbital, you can have different types. And for example, physicists are mainly familiar with the p-n junctions, but you can also have type 1 heterojunction in which you have energy transfer from the donor to the receptor, or type 2 is probably the most common one, when you have charge transfer. And there are also some different ones, but they are mainly important for catalysis. For type 1 and type 2, you can have different photoinduced phenomena. For type 2, if you excite the donor, the electron on the donor can be transferred to the acceptor. You have photoinduced electron transfer, and the same you have for the hole. For the energy transfer for the type 1, you at the same time you can have the excitation of the donor and the acceptor electrons, and then you can swap to have energy transfer. And this can be a bit more complicated. You can have different kind of energy transfer, like the most common is the Forster's one, where you have excitation and de-excitation on the same molecule, the same donor or acceptor. You have the Dexter, when you have the transfer to of the electron from one fragment to the other. I also have the triplet case. So I will give you today an example of what we do in this kind of studies. We consider a 0D interface is based on an azobenzene derivative and one of these nanographene or large pH. The graphene we consider is has an amino substitution in para and is linked through a linker to a pyridine to ensure the pi-pi stacking with this nanographene. And what we do, we consider DFT calculation, we optimize this interface, but also we go a step forward. We consider an assembly of this nanographene on graphene to consider the thermal effect. Then we extract different frame from this molecular dynamic simulation, and we do electrostatic UMMM. And on each frame, we calculate the electron copy, ionization energy, driving force to get the macro theory for the different photo-induced processes that I mentioned before. I will spend here a minute to talk about the electronic coupling, because we use a relatively new method that is called, multi-state fragment charge transfer fragment excitation fragment excitation transfer. So it's this, and it sounds complicated, but essentially it merges together the fragment excitation difference method and the fragment charge difference method, and it considers there's different matrices that are put together to generate a new matrix, is diagonalized, and then at the end of a series of additional diagonalization, you have the adiabatic term in the diagonal of this matrix for the charge transfer for the local excitation, and this is then diabatized. So what we consider is the diabatic coupling starting from the adiabatic picture. And the advantage of this is that with this diabatization procedure, you can use a large number of excited states. In this case, we use around 40, and we can have a complete demixing between the excitation of different nature. So we can reconstruct which excitation is local, which is charge transfer, and so on. And if you want to more detail, I strongly suggest to read this paper. This very well describe all the derivation, the procedure for the calculation of this coupling. Okay, so why azobenzene? Azobenzene, it looks like a very straightforward molecule. It's pretty easy. It's known studied since probably 100 years, and they're still studying it because despite its relatively straightforward structure, it has extremely rich chemistry, physics, and also photophysics. And the main idea is that when you start with the transurobenzene, you can shine light and you obtain the cis that is metastable, that can revert back to the trans either thermally or with an input of light again. And those can be very long lived states, and it is a kind of archetype for the photoswitch. But the intriguing part is that azobenzene is a non-Kasha, doesn't follow the Kasha rule for the excited state. So the first excited state is an n-pi star transition that is forbidden, and the first bright transition is the second excited state that is a pi-pi transition. So, and still is not extremely clear what is the mechanism of action going from the trans to the cis. It is known more or less in gas phase, but when you put an environment, different kind of liquids or biological environment, is still challenging and not clear what is the mechanism of action for this photoisomerization. So what we do here, we focus first on the intrinsic charge transfer of this azobenzene derivative. Here I report the absorption spectra, and you see for the trans we have the pi-pi peak. For the cis we observe the m-pi because due to the distortion the cis has a small dipole moment, so it can be accessible. And we compute the key parameter for the Marcus-Rite equation, and what we observe is that the excitation energy transfer is the process that is more probable to occur, and is much higher for the trans azobenzene compared to the cis. So if we then put the interface together, we can already see from the picture of the alignment of the energy level that this should give to energy transfer. And indeed, what we observe is that the energy transfer, excitation energy transfer, is the predominant process. This is due to the fact that the presence of this nanographene strongly increases the organization energy, because you can easily add one electron or remove it without strongly modify the structure, due to the fact that it has so many pi bonding, you can accommodate one more electron. And it's the electron transfer, the energy transfer is much faster than both electron and hole transfer. So say, great, this is it. We have the picture, but actually no, because it's a kind of model system. The system was optimized. So what happened if you go a step closer to what is done in an experiment? So we add also the thermal effect. So for this we retrieve to the molecular dynamics simulation, and we did we extract them different amount of frame to do QMMM. And what is observable here is that we have an interesting increase in photoinduced Hall transfer for both cis and trans, and is now for the cis is became the main processor, while for the trans is comparable with the electron energy transfer. And with that, this I think you can read yourself. My the take-home message for is that the simple picture of alignment of an energy level is good, is great, but it's not everything. So pay attention when you study different interfaces, because it can be misleading when you consider a bit more complex method. When you add thermal effect, perhaps your solvent, it might also change. And with that, I would like to acknowledge the people, particularly Magdalena, that did the work, the collaboration in Italy, the founding, and thank you for your attention.
Thank you. Yes, so the first question.
Thank you, very nice talk. I was thinking maybe, like, did you try any other levels of theory? Because TDFT is known not to be very, very good for charge transfer states, so maybe double hybrids or anything.
At this moment, no, because the system is pretty big also.
Yeah.
So already the nanographene is around 150 atoms, so you cannot really do more.
Can I do a follow-up? So you have effectively like a Weber coupling Hamiltonian. Have you tried to run dynamics on it?
No, not yet.
Because that's something that should be straightforward and very fast. So.
This is something that we are planning for the next step, let's say.
Really interesting work. I really like it. Thank you.
Thank you. Any further questions? I don't see any. So Silvio, many thanks for your contribution.